We can use source transformation to determine the value of something we need in a circuit by repeatedly source transforming until our circuit is extremely simple. Before we go into the circuit, I wanted to point out this dependent element. This dependent element creates a current based on the value of some other part of the circuit. This is useful for modeling certain more advanced electronic devices such as transistors, but basically you can just treat this as a current source that produces a current of 0.25 Vx. And since it's an unknown that's somewhere else in the problem, it'll eventually clear itself out. It is helpful when source transforming to try and turn the circuit either into a circuit where all of the resistors are parallel or everything is in series. Remember that we can convert the following two forms of a circuit to each other. Notice that in this form, the current source and the resistor are in parallel. We observe that occurring here, and they have a shared A and a shared B. We can see that we could consider this A and this B. The conversion is as simple as V equals IR, retaining the same R. So this portion of the circuit can be turned into a 4 ohm resistor, I'm going to put it off to the right here, and a voltage source, which is I times R, so 0.25 Vx times 4, which is of course just Vx. And so this whole section of the circuit from here to here has been turned into this circuit instead of these two parallel wires. And so we can write this circuit as follows. You can see that these circuits are basically identical, except that right here has become right here. This circuit would still require mesh analysis, so I'm going to try and continue to convert it so that either everything is parallel or everything is in series. In fact, I'm going to do it both ways. To make everything parallel, I'll begin by source transforming the 6 volts and 2 ohms. 6 volts divided by 2 ohms, V over R, equals 3 amps. So we should have a 3 amp current source and a 2 ohm resistor that is parallel with it. And it looks like we have this other 2 ohm resistor from here that's also parallel. Now observe that these two voltage sources can be added together. They are both in series and they have the same negative positive terminals, so they can be added together as 18 plus Vx. Then once again, that can be source transformed into 18 plus Vx divided by 4 is the current source, because 18 plus Vx divided by 4 is V over R. Note that 18 plus Vx over 4 is 4.5 plus 0.25 Vx. And then, of course, we'll fill in the 4 ohm resistor in parallel instead of in series because the source transformation has occurred. Finally, we can add these two current sources together into one. Why can we do this? Because this whole thing is one node. Each of these current sources is inputting into this node. Each of these current sources are outputting from this node. Because they input into the same node and output out of the same node, they can be treated as one single current source. Note that the voltage drop Vx is still over any of these resistors. That's the really convenient part. The voltage drop across this 2 ohm resistor is the same as across any of the 2 ohm or 4 ohm resistors. To finish solving this circuit, I'm going to use Kirchhoff's current law on this node, and I'm going to set a ground right here. You'll notice that the current across each of these resistors is simply Vx divided by that resistor. So into this node is going this current source, and out of this node are going Vx over 2, Vx over 2, and Vx over 4, so KCL's law is 7.5 plus 0.25 Vx, or the current going in, equals Vx over 2 plus Vx over 2 plus Vx over 4. This is equivalent to 0.5 plus 0.5 plus 0.25 Vx. We can cancel out these Vx's to get that 7.5 equals 0.5 plus 0.5 Vx. And we now know that the voltage is 7.5 volts. Observe that I ended up using nodal analysis at the end because it was convenient. I mean, it was a single node. Really, I was just using Kirchhoff's current law and Ohm's law, but using Kirchhoff's current law and Ohm's law is the essence of nodal analysis. Now we'll source transform this circuit so that everything is in series instead. To do this, we actually need to convert this to temporarily be in parallel instead, so that we can subsume this 2 ohm resistor. You'll see what I mean in a bit. Just like before, we convert the 6 volt and 2 ohm resistor into a 3 amp current and a 2 ohm resistor. I'll also combine the voltage sources immediately into just 18 plus Vx for convenience. Now to get rid of these two parallel resistors, because I turned this 6 volt and 2 ohms into a set of 3 amp and 2 ohm parallel resistors, I can just combine the two parallel resistors into one. Note that to do this, we simply say 1 over 2 plus 1 over 2 equals 1 over R equivalent. 1 half plus 1 half is 1, so R equals 1. So we can rewrite this circuit as having a 1 ohm resistor in place of the two 2 ohm resistors, and of course we have the rest of our elements. Note that the voltage across this 1 ohm resistor is still Vx. Now we will reconvert this parallel system into a series system by multiplying I times R to get 3 volts and of course 1 ohm. Now the question is, where is Vx now if there's no 1 ohm for it to be over? Note that Vx was between these 2 points. When we convert 3 volts, 3 amps and 1 ohm to 3 volts and 1 ohm, Vx is still between these 2 points. You can see how they are the same in the 2 circuits. Now let's observe a couple things concerning Vx. Let's suppose that this is a ground. Then this point is 18 plus Vx. And if we suppose that this is the current I, then there is a voltage across this 4 ohm resistor that I'll call V4. So this point has a voltage 18 plus Vx minus V4. Because this whole circuit is in series, there is one current throughout the entire circuit. So we can simply determine the current by dividing the total voltage by the total resistance. Note that these two voltage sources are in opposite directions along the circuit, so we subtract them. Note that our current is in this direction, so we'll choose this voltage to be positive. So our total voltage is 18 plus Vx minus 3, and our total resistance is 5 ohms, and thus our current is 15 over 5 plus Vx over 5. That is equal to 3 plus 0.2 Vx. And now that we know what I is, we can multiply I times R to get V4. So V4 is equal to I times 4, which is equal to 12 plus 0.8 Vx. So we know that Vx is equal to 18 plus Vx minus V4. We know what V4 is, so let's substitute all of this into an equation, which I'll do a little bit higher. Vx equals 18 plus Vx minus all of this, 12 plus 0.8 Vx, which gives us 6 plus 0.2 Vx. Then we subtract 0.2 Vx to get that 0.8 Vx is equal to 6, and therefore Vx equals 7.5 volts. You see that we've gotten it right both times. Notice that in this problem I used another methodical approach. I put down a ground, and then I just started adding and subtracting voltages until I figured out what Vx was compared to the ground. This is close to KVL at work, because I also use the fact that the current through the entire loop is the same. So when you source transform a circuit so that you have a full loop, you can exploit the fact that the current is the same throughout the whole loop. Add together all the voltages, add together all the resistors, and get the current, and then the current can help you do stuff. This is the kind of problem that counts as an advanced problem for a T2 because it really tests your problem-solving abilities, and it's actually helpful in a T4 for you to think through your process of having solved this problem. The T2 should explain your problem-solving process, but if you notice something about the way you think, or the way you personally problem-solve in general, that's a great thing to think through for a T4.